everyone, I am Miss Hu, your physics teacher. In this video, we're going to go through some tips on how to answer the IGCSE Physics Paper 6, which is an alternative to Practical. So this video is for students who are taking Paper 6. If you are doing Paper 5, this video is not for you. So please watch my video on the tips on how to answer IGCSE Physics Paper 5 instead. I'll put the link in the description below. First of all, let's go through what Paper 6 is. In terms of the format of Paper 6, it's made up of 4 questions which total 40 marks. You are given 1 hour to finish this paper, and the marks for this paper will constitute 20% of your entire grade. The 4 questions in this paper are made up of 3 practical-based questions which are worth 11 marks each, giving you a total of 33 marks. One of the questions usually requires a graph. The 4th question is a planning question, which makes up the remaining 7 marks. We will cover the planning question in another video because that question is also within Paper 5, so I've made a separate video for this planning question for both Paper 5 and 6. Now, these 4 questions are usually from different units. Now, about this paper. This is a technical paper. For Paper 6, you do not need to conduct any experiments to answer this paper. In fact, you are given the results of the experiment. From those results, you will need to record and analyze the data, as well as write a conclusion and all other necessary complementary information, such as precautions, discussions, and others, depending on what the question is asking. Because the data is already given, there is no range of data and no room for errors. Your answers must be the same as what is in the mark scheme except for the open-ended questions. Because this is a technical paper, the way you present your data is important. So it's not just about what values you have, it's how you present it. Now, before we go into the tips,
let's go through some general advice about what you should or shouldn't do when it comes to this paper. First of all, let's start with time management. You're only given 1 hour to complete this paper, and because this paper is made up of 4 questions, the suggested time allocation is to spend 15 minutes on each question. Of course, it's possible for you to spend more or less time on each question. This is just a suggested time allocation. As long as you're able to answer all the questions within the 1 hour, that's fine. Now, first of all, let's talk about your stationery set which you will need to bring in. You can only use black or blue pens for writing your answers. You must also make sure you have a pencil, preferably HB, because all drawings must be in pencil. Now, the drawings that you may have to do in your paper may include graphs, diagrams, and even lines, such as connecting lines or lines for a table. Anything which you need to draw must be in pencil. You'll also need to bring an eraser just in case you need to rub off any mistakes that you made with the pencil. Make sure you also bring a short or long ruler because any lines you draw should be drawn with the assistance of a ruler. Remember to also bring a scientific calculator, a protractor, and all of your stationery must be in a clear, transparent case. Now, do not bring the following because you are not allowed to use any colored pens other than black or blue. So don't try to stand out from the crowd by bringing an orange or green or pink pen. It will be stated very clearly on the cover of your examination paper that you can only use black or blue. And in fact, all the practice questions you've been doing up to now in school or at home should have been in black or blue only. You are also not allowed to use erasable ink. Now, I know that in the stationery stores, you can now quite easily buy a pen which comes with an eraser at the back to erase the ink on the pen it comes with. This is not allowed, and in fact, it puts yourself at a great disadvantage. Why? Because the problem with erasable ink is not that it's erasable, but rather the ink fades with time. I have seen some papers where students have written the answers with erasable ink, and in less than 1 week, the ink had completely faded, so much so that the paper looks completely blank. So if you were to use that kind of ink for your exam paper, you got to remember that by the time it gets to the examiner, it could be more than 1 week later. All the examiner is seeing is a blank piece of paper, and it doesn't even have your name or code on it, which means that effectively it is as if you have never sat for the paper, even though you turned up in the exam hall and spent that hour and 15 minutes writing a lot of things. And yes, that means you'll get a 0 for this paper. So do not take the chance, do not use erasable ink. Now, you're not allowed to use a highlighter in your examination paper, and you also cannot use any correction tape or fluid. For the highlighter and correction tape or fluid, this is also already mentioned in the instructions on the cover of the examination paper. If you're thinking, how do we make a correction if you made a mistake in your answers? All you do is you take your pen, just put a line through the answer you have made, and rewrite your answer at the side. Look, the examiner is quite smart. They're going to be able to see where your actual answer is. Now, all of these refer to the stationery you are not allowed to use. So it's not that you're banned from bringing them into the exam hall, but there's no point bringing them in because you can't use them anyway. So don't pack this in your list. However, there are some things which are banned outright. If you bring them into the hall, they will be confiscated, or if they're found on you during the exam, you could be written up as cheating. So make sure you don't bring in any of these following. You cannot bring in your calculator cover or calculator case. Why? Because some calculator cases have equations written on them. You are not allowed to bring in an opaque stationery case as well. The reason is very obvious. Some students may try to smuggle in crib sheets and try to hide them in that case. A crib sheet basically is a small piece of paper with information written on them to help them answer the questions in an examination. You're also not allowed to bring in any devices into the examination hall with you, and this includes phones, tablets, laptops, even smartwatches. Anything else besides this list, don't bring in. Now, some suggestions on what you should do before the examination. Make sure you get enough sleep. I've had students in the past who tried to pull an all-nighter by staying up studying, and what happened was they got so tired. One, they actually end up being late for the examination. Now remember, if you start late, they're not going to give you any additional time. If you come in late, depending on how late you are and whether the chief invigilator wants to let you in, you will have to finish exactly on time with the rest. So for example, if you come in 15 minutes late, you will have 15 minutes less to answer the questions in the paper. Now, even if you're there on time, if you're too tired from pulling an all-nighter, you're not going to be able to focus and think of the correct answers. I've even had students who fell asleep during the examination because they were way too tired. So do not do the silly thing by trying to stay up all night. Make sure you get enough sleep. Be early, not on time, because when you're there early, you're able to calm yourself down, settle your mind, and prepare mentally to do well for the exam. Sometimes when you're just in time, you might still be in a bit of a panic, and that's not a good start for your examination. Before you even leave the house, make sure you have everything you need for the exam. Make sure you have the complete stationery set as mentioned in the previous slide. So all your pens, your sharp HB pencil, ruler, eraser, protractor, your calculator with fresh batteries because you don't want your calculator to run out halfway when you're trying to do the calculations. And also make sure you have your ID and exam slip to prove to the invigilator that you are who you are. Also, make sure that you go to the washroom before queuing up to go into the examination hall. Now, although some invigilators may allow you to go to the washroom during the examination, you know that every minute you go to the washroom, that reduces the time you have to answer the questions. Look, it's only an hour and 15 minutes. I'm sure you'll be able to last through the entire time without visiting the washroom. So make sure you empty your bladders before you go in. My suggestion, only go to the washroom if it's a real emergency. At the start of the exam, make sure you follow the instructions of the invigilator. Don't try to do anything before the invigilator gives you the instructions to. Now, usually the instructions given by the invigilators would include checking that you have the correct examination paper. If you're in there for a physics exam and you've got a paper for chemistry, don't open the paper and start doing it. You gotta let the invigilator know, wrong paper. Now, the invigilator will also give instructions to all of you on when you can start writing your name, center number, and candidate number on the examination paper. Only write all this when instructions are given. During the exam, make sure you stay in your seat. Do not attempt to try to stand up, walk around, or look around. If you need something from the invigilators or assistance of any sort, raise your hand. The invigilator will come to you. Do not walk to the invigilator. This is because if you walk around or look around, this actually indicates that you are trying to cheat, because by walking or looking around, you'll be able to see the answers on the other candidates' papers. At the end of the examination, Put your pens and pencils down when instructed to. Tie your papers up if you need to. So for example, if you needed additional examination paper, you need to tie them up together so that it is one set which can be handed to the examiner. Stay in your seat, wait for your paper to be collected. You may only leave the examination hall when instructed. So all of these are the general do's and don'ts when it comes to examinations. There may be some differences depending on your examination center, but no matter what, just make sure you always follow the instructions of the invigilator. Now, when it comes to asking for assistance during the examination, do not ask the invigilator for assistance unless absolutely necessary. Any unnecessary questions will be dismissed. Persistent questioning will be written in the vigilator's report, which can cause marks to be deducted from your grade. For example, if you try to ask the invigilator to clarify any part of the content of the question paper or for any answer to the content of the question paper. Now, there may be exceptions only in very special circumstances. For example, if special access arrangements are required by the student. Special access arrangements are for students with disabilities. So for example, they have trouble reading the paper or they're not able to write. Usually, this kind of special access has to be arranged in advance and only by students who qualify for the special access arrangements. Now, what kind of assistance can you ask for which will not cause any mark deduction? As long as, of course, you're not asking for any help with the question paper itself. For example, if you're asking for additional writing paper, this might be needed, for example, if you run out of space on your exam paper. That's fine. Now let's go through generally the typical questions you would need to answer. So what we'll be looking at in the next few slides are some extracts from past year papers. So we're not going to go through the entire question, nor are we going to go through the answers in detail. We're going to look at some of the typical kind of questions that you would need to answer. So one of the typical kind of questions you would need to answer would be to complete the table of data. These are extracts from questions 1 and 2 of Winter 2024 Variant 1. So the table for question 1, as you can see, has incomplete headers and some incomplete cells, while question 2 has incomplete headers. So you would usually need to complete the headers by writing out the missing units. For the incomplete data in the table, normally the question would tell you which diagrams to look at in order to complete the data. So don't miss out on writing the units because I consider these as free marks. Just by writing the units in, so for example, this would be seconds, seconds, and seconds squared, that would already give you 1 mark. Likewise for question 2, this would be seconds and degrees Celsius. Just by writing the units, you can already get 1 mark. Another kind of question you would normally be required to answer would be to record the measurements. So as I mentioned earlier in this video, you would be given the data, you would just need to record it. Again, I consider this as free marks provided you read and record them correctly. So an example would be like these question extracts from Winter 2024 Variant 2. In question 1B1, the student uses a balance to measure the mass M of the covered stack of slides. You need to write down the mass of the covered slides to the nearest 0.1 grams as taken from the balance in figure 1.3. Now here's the thing, the common mistake a lot of students make is that they write down the number on the balance as is into the space here. That means they write 57.87 straight away. But the question has already said you need to write it to the nearest 0.1 gram. So you need to round this value to the nearest 1 decimal place. That means that the value you need to write here is actually 57.9. So it's really easy as long as you follow the instructions. Like I said, I consider this a free mark. Just like for question 2, the voltmeter reading is shown in figure 2.2. You just need to take the reading and record the value in the top row of table 2.1 under the heading of VPQ. Just follow the instructions by reading the values correctly and recording that value. Now, in addition to recording measurements, sometimes the question may require you to take measurements. Now, obviously, in this kind of theoretical paper, the only measurements you can take are length measurements using your ruler. So for example, we have question 3 from the Winter 2024 Variant 1. They give you a diagram here, figure 3.2. You need to measure the height h0 of the illuminated object. On the right hand side, we have question 1 from the Winter 2024 Variant 2. Figure 1.2 shows side views of the taped stack of slides given to the student. This figure has been drawn at full scale. Using figure 1.2, measure the length, the width, and the height of the covered stack of slides in centimeters to the nearest millimeters. So for these questions, you need to use your ruler, take the measurements directly from the figures because these figures are all drawn at full scale. So in this case, you are tested on whether you're able to take the measurements using your ruler and recording them correctly to the nearest millimeter of your ruler. Now, you also need to be able to estimate actual values. So for example, in this extract from Winter 2024 Variant 1, question 1 shows you the setup of a pendulum experiment. So this question does explain what the experiment is about and some various values with regards to the setup. But you have a question here in G where it tells you the pendulum support is 40 centimeters above the bench and you need to estimate the distance x between the bottom of the pendulum support and the floor. So you need to be able to estimate the value of x given this setup and other values. So even though you don't have the actual experiment, it is based on your practical experience where you should be able to estimate this value. As you can see, the mark scheme is a bit open-ended. It accepts a value between 100 and 140 centimeters. Because as you can see, this value is based on the values I've given you here at the beginning of the question where it tells you D is about 90 centimeters. Now, in addition, it also says that a student plans to plot a graph of t squared against d, suggests suitable values of d that the student can use to obtain measurements that are sufficient for this task. There are no fixed values in this case. It is open-ended. They want you to write at least 3 additional values which are logical, and the value should not be greater than the distance of x that you have stated here in G, because obviously, if the value was greater than x, your pendulum cannot oscillate. So although this is a theoretical paper, it is based on practical knowledge, which includes the ability to estimate actual values. You can also see this in this example of the question taken from Summer 2024 Variant 1. The student plans to plot a graph of resistance R against length D to test the suggestion. So this is an experimental question. Suggest suitable additional values of length D to use. And you can see from the answer here, it's again open-ended. They want you to write at least 3 additional values, and all values quoted are more than 0 and up to 100 centimeters. Because whenever you do length experiments for resistance wires, we usually go up to 100 centimeters because we are using the meter rule. Now let's look at drawing graphs. Now, when it comes to drawing graphs, there's usually at least one graph question in paper 6. Not guaranteed. There are some past year papers where there are no graphs, but one graph question is rather common. So when drawing graphs, all you need to do is plot the graph based on the values given here in the table and follow the instructions in the question. Sometimes they're very kind. They give you a graph with already the scale all drawn out for you. You just need to label the axis. So as you can see, it says here plot a graph of VCM on the y-axis against UCM on the x-axis. They've even told you what should go on the y and x-axis. So you just need to label the axis, plot the graph, and draw the best fit curve as they've already told you within the question. So you know this is going to be a curve. Now this kind of setting is not going to be in all questions. It's more likely they'll give you a blank piece of graph which you would need to plot from scratch. So for example, for this question, it tells you to plot a graph of temperature theta against time. They've even told you what should go on the y and x-axis respectively. So theta goes on the y-axis and t goes on the x-axis. They've even told you you do not need to start the y-axis at 0 and to draw the best fit curve. So the instructions are very clear. All you need to do is just draw a graph by following the instructions. It's an easy 4 marks provided that you follow what they want. Now, one thing to take note, when it says you do not need to start the y-axis at 0, never do the heartbeat thing. What I mean by the heartbeat thing is this. So a lot of students learn in math that when you want to start a scale from a number that's not 0, you can draw this little jagged thing to show that it skips. So for example, for theta, we don't have to start from 0. So let's say we want to start from 70. So I have a lot of students who do this. They go 0 and then they do this little jagged thing and then jump to 70. You don't do this heartbeat thing as it's called because it looks like a heartbeat. Now, this is not allowed in physics. We don't do this because this would get in the way of us getting the correct gradient value. So if you want to plot the graph, for example, we know that t for the x-axis can start from 0. You can start from 0 and move on here. For example, you could go 0, 0.5, 1.0, 1.5, 2.0, 2.5, and 3.0. This would be t for seconds. However, for theta, which is the y-axis, we don't have to start from 0. So if you look at the numbers, you could potentially start from 70. All you need to do is just label the bottom line as 70 straight away. So you don't have to do any jagged skipping numbers and all that. Just start from 70 and continue the label upwards. So for example, for theta degrees Celsius, you could go 70, 75, 80, 85, 90, 95. So just put the number directly. You don't have to skip numbers to show that the scale is not starting from 0. So this is true even if both axes do not need to start from 0. So you do the same thing at the origin. You don't have to start from 0. For example, for this graph, now this cell is blank because you're supposed to read it from the diagram. Let's assume that you can start from 0.20. So we just start from 0.20 here. So you can go 0.2, 0.25, 0.3, 0.35, and 0.40. So you don't have to do any skipping heartbeat thing. You don't have to have the same number at the origin. If this is for current of ampere, then this would be LCM, and you can start from 20.0. Origin does not have to be the same for both the x and y axis. So sometimes you may be required to draw a best fit curve, sometimes you need to draw a best fit straight line. The good news is that the question would normally tell you what kind of shape to draw. If let's say your question doesn't say so, then you need to look at the trend of the points and plot the graph that best fits that trend. So generally, regardless of whatever shape of graph you're going to draw, there are 4 marks given for drawing the graphs, and these are the points that you need to get correct in order to score those marks. 1 mark is given for labeling the axes correctly and the right way around. So your axes should have the symbol with units, and you must also draw the axis lines. That means that your graph must have the axis lines with the symbol and units. For example, LCM and I ampere. I have some students who are so lazy, they don't even want to draw the axis lines even though it takes them less than 1 second to do that. If you don't draw the axis lines, you may not get the marks because you need to show clearly where your axes are. Now you need to also make sure that you have a suitable scale.
Suitable scales here, of course, refers to the scale of both the y and x axis. The scale number should always be in multiples of 1, 2, or 5. So what I mean by this is the scale could be 0, 1, 2, 3, 4, 5. It could also be 0, 2, 4, 6, 8, 10, or it could be 0, 5, 10, 15, 20. Now, variations of these scales are also accepted. For example, if you go by 4, 0, 4, 8, 12, because these are multiples of 2. Tens are also accepted because they're multiples of 2 and 5, 0, 10, 20, 30, 40. Do not use odd numbers, which makes it very difficult to determine the scale. For example, multiples of 3 or multiples of 7, 0, 3, 6, 9 or 0, 7, 14. Can't we use multiples of 15 because 15 is a multiple of 5? No, because 15 is also a multiple of 3. Here's the logic behind determining the scale that you use. The idea behind the scale is that it makes it easy for us to determine the values in between. That means to interpolate the data. Let's say you want to determine the position of the value of 1.3. It's quite easy because between 0 and 2, you just need to take 2 divided by 10 squares. Each square is 0.2. So to determine where 1.3 is, it is in between the 6th and 7th deviation. So if you had a number like between 0 and 4, it's actually also quite easy to determine because between 0 and 4, each square would be 0.4. So 1.3 would be a little more than the 3rd deviation. But if you pick a number like 3, if you want to find the position of 1.3, it becomes rather awkward because it's difficult to divide even these small squares into smaller deviations. So while not impossible, it's awkward. So you'd be like, okay, 3.61. 0.1.2 maybe is roughly here, but it's awkward to find. Possible, but difficult. And if you chose a scale like 7, it's even more difficult because it's harder to divide that smaller square into smaller deviations. So that's the logic behind choosing the scale. So that's why we don't pick 3, we don't pick 7. Remember that suitable scales, we usually use multiples of 1, 2, 5. I think I'll just add 10 here just to make this more complete. Now, in addition to choosing the correct scale, you also need to make sure that the range of scale that you have selected makes the graph large enough. So the rule of thumb is that the minimum and maximum number should cover more than 50% of that axis. What do I mean by this? So depending on the values that you've obtained. For example, if on the x-axis, the values you have range between 50 to 70, that means that 50 to 70 should cover more than half of the x-axis. So if you were to do something like this, let's say you've got 50, 60, 70, 80, 90, and 100, this would already be incorrect because as you can see, 50 to 70 only covers 40% of the x-axis. So instead, you need to spread this out. So for example, 50, 55, 60, 65, 70, 75. So even though 70 may not reach all the way to the end of the x-axis, but you can see between 50 and 70, it now has covered 80% of the x-axis. And you need to make this true also for the y-axis. Why? Because normally the rule of thumb is that the graph you draw should cover more than 50% of the space of the graph. The problem with a lot of students is that their idea of 50% is not the same as the idea of 50% of the teachers or examiners. They tend to draw much smaller graphs than 50%. So by forcing the range to cover more than 50%, that way they can make the graph to be bigger than 50%. A rule of thumb I always tell the students is try to draw the graph to cover at least 75% of the graph size, because that way it'll be more than 50%. 75% is not a requirement, but it is a size that you can aim for because that will guarantee you it'll be more than 50%. In fact, I always tell the students, go big or go home. Try to draw the graph to be as big as possible. That means the two extreme points of your coordinates should try to cover as big a space as possible. So of course, in between, the points could be scattered anywhere, but your two extreme points should be as far away from each other as possible and cover the maximum area of the graph space. Because the bigger the graph, the more accurate it will be, and there's a higher chance of you making sure you are able to fulfill the scale requirement. Other marks are given for correct plots. That means you've plotted the points correctly based on your data collected. And the last point is given for the best fit line. That means you've made a good judgment in terms of drawing the best fit line. And the line must be thin and continuous. So one straight line. Don't try to feather it with different lines. That's going to be marked wrong. And don't use a thick pencil. If you're drawing a curve, then make sure the curve is continuous without any kinks. So not, oops, this would already be marked wrong. So one continuous line, whether you're drawing a straight line or a curve.
Now, other kinds of analysis could include, for one, to determine the gradient of the graph that you have drawn. So for example, if we take a look at this question asks you to determine the gradient of your line and to show all working and indicate on the graph the values that you use. So on the right hand side here, this is just a sample graph. It's not a complete graph, but we'll just use this as a reference on how to show the gradient of your graph. When it says here, show all working and indicate on the graph the values that you use, what you need to do is to draw the gradient triangle. Ideally, the triangle should take up more than half the distance between the extreme points, but my recommendation is, as I mentioned earlier, go big or go home. So try to get the size of the triangle to be as large as possible. Why? Because remember that for students, your idea of half the distance might not be the same as the idea of half the distance of the teacher or the examiner. So by taking the largest possible triangle, you guarantee to get a size of the triangle that's more than the minimum size recommended. So in this case, indicating on the graph here means to draw the gradient triangle. Some students don't want to draw the triangle. They thought they could just indicate on the graph by marking 2 points on the graph and writing the coordinates out, and that would be how you indicate. That's not correct. Marking the points and writing the coordinates out indicates nothing. So don't do that. Now you also need to show your working, which means that you need to write out the formula for the calculation of the gradient. So depending on which formula you use, you could be using m equals y2 minus y1 over x2 minus x1, or you could use rise over run. Both will get the same answer. In either case, the coordinates that you use in your calculation must be the two coordinates on the extreme points of your gradient triangle. You cannot just draw a random triangle and take two other random points on the line. The 2 points that you put in your formula must match the two coordinates of the gradient triangle. Remember also that the gradient has a unit. So some students will argue with me, gradient, there's no unit. Remember, this is physics, everything has units. So what is the unit of the gradient? It depends on the graph that you are given. To determine the unit of the gradient, you need to get the unit of the y-axis over the unit of the x-axis, just like you see in the formula over here. So for example, if this was LCM and I ampere, the unit for the gradient would be centimeter per ampere. So whatever value you got from the gradient calculation, you put in here and make sure you write the unit as well. Now another kind of graph analysis would be to interpolate the data. So for example, this question here asks you to use your graph to find the value of V when U is 30.0 cm. Show clearly on a graph how you obtained the necessary information. So to interpolate here means that you've already got the graph plotted out. You need to find the value of one of the variables given the other. So for example, if this was a V versus U graph, to find the value of V, you need to look up the value when U is 30. Let's say this is 30. You need to draw the dotted line out to look up the value of V. So whatever value you get from the graph, you need to write it in the space provided. Obviously, this line should be drawn with a pencil and a ruler. So when it says show clearly on the graph here, you need to draw this line. This would give you 1 mark, and 1 more mark will be given for the correct answer. Now let's take a look at some precautions that you need to know how to write. Now the precautions we're referring to here are not safety precautions, but rather precautions here normally refer to how to improve the accuracy of the experiment. So here's an example of a precaution on taking the reading. Explain why it is good practice to read the thermometer scale at right angles to the reading. So this is with regards to placing your eye position at the correct angle, and yes, this is about avoiding parallax error. So sometimes the question could ask you to explain, meaning they want you to write out the name of the error, or they could ask you to describe the technique instead. Like you can see here, describe one technique to use so that the temperature reading is as accurate as possible in this experiment. And in this case, you don't write avoid parallax error, you write about how the eye should be positioned. That means you view the temperature scale perpendicularly. So although both questions are about the thermometer, bear in mind that these are the answers you would write regardless of whatever measuring instrument that you would be using. So whether it's a thermometer or a meter rule or any other kind of measuring instrument. Now besides this kind of precautions, you could also come across questions like these. Suggest one possible source of inaccuracy in the procedure even if it is carried out carefully. Or they could phrase it this way. Suggest one practical reason why other students might not obtain the same result as this student even if they do the experiment carefully. So you can see that in both questions, they mention that the experiments are carried out carefully. So these are not referring to errors in execution. That means there is no human error, for example, a parallax error. So these kind of questions are actually asking about problems within the method of the experiment. To get the answer, it depends on the experiment that is being conducted. So you need to think about what is it about the procedure that could be the problem. That means no matter what the student does, there's still going to be an inaccuracy in the results. There are no fixed answers for these. You need to use your practical knowledge to figure out the answer, which is why I'm not sharing with you the answer from the mark scheme, because these answers are unique to the respective experiments. Another kind of precaution you might come across would be to suggest one technique to use in this type of experiment to ensure results are accurate. So the answer you're looking for in this experiment is not the parallax error answer. Why? Because the question says in this type of experiment, which means that you need to find the unique precaution specific to this kind of experiment to make sure that the results for this sort of experiment are accurate. Now, what are some of the possible answers for this question? We're going to take a look at some of the experiments shortly in this video. For now, I'll just move on to the next part, which is the statements and justification. So this is also a very common type of question that comes out. For example, if you look at this question, write a conclusion describing the effect of changing the size of the beaker on the rate of cooling of the hot water. Justify your answer by reference to values from the results. So obviously you need to write a conclusion about how changing the size of the beaker will affect the rate of cooling of the hot water. The thing is, not only do you write a conclusion, you must justify the answer. So when they say justify your answer, you must mention values from the results. You cannot just write the conclusion and write a general explanation. When it says here by reference to values from the results, you have to write actual numbers from the results in here. Whether it's writing the actual numbers out, any calculations or side-by-side comparisons, you must write the values from the results as a justification in your answers in the space provided here. So this is quite common, as you can see in this question from another paper. State whether your results support this suggestion and justify your statement by reference to the results. Again, you must justify with reference to the results. That means put in the results, whether you're writing a side-by-side comparison of numbers or any calculations, you've got to write them out here in the justification section. So not only do you need to refer to the results, sometimes you need to refer to the graph. So for this question, a student states that the average rate of cooling of water decreases as the temperature of the water approaches room temperature. State whether your graph line supports this suggestion. Explain your answer by reference to the shape of the graph line. So again, because you need to refer to the shape of the graph line, whether the line is a linear graph or a curved graph, you need to talk about the shape of the graph and explain how this graph line supports this suggestion. So the mark scheme for the statement justification here are a little bit more open-ended, as long as you're able to give the answer as what the question asks. For example, the shape of the graph line, or with the values from your results, you should be able to get the mark. Now, let's go through the precautions unique to specific experiments, as I had mentioned earlier. Do take note that this is only a general extract, and this list is non-exhaustive. So, for the alternative to practical questions, that means for questions 1, 2, and 3, you must know how to read and take general measurements. Regardless of the experiment, you just need to follow the instructions in the question. The questions usually test your ability to take measurements in general. So we're not going to go through all the experiments, just some precautions for specific experiments. Why? Because as long as you can follow the instructions and you know how to take measurements, you should be fine. You're not actually conducting the experiments. So let's go through one of the common questions that come out. Balancing masses on a meter rule. So this normally involves balancing a meter rule on a pivot and placing a mass on one side or both sides of the meter rule. A common question is, how do you ensure that the center of the mass is at the correct position? Because the mass that's normally provided is opaque and it will be blocking the numbers on the meter rule. So how do we make sure that the center is where it's supposed to be? So the answer you should write is actually a practical, logical answer. So think about how you do this in real life and write that out. So if you're not sure how to write it out, let's take a look at how the sample answer is in the mark scheme. So it says here, take a scale reading at the left and right hand side of the mass and ensure the average is the value that you're looking for. So I've put here as XCM because whatever value you write here, you just write down the value that you're supposed to place the mass at. So for example, if the mass is supposed to be placed at a 90 cm mark, then you write 90 cm over here. If it's supposed to place at a 2 cm mark, you write 2 cm over here. Even if you don't use these exact words, but you write words to that effect, you would still get marks for this answer. Another common question would be to suggest one practical reason why it is difficult to obtain accurate readings. So in this case, why it's difficult to obtain accurate readings is because if you had conducted this experiment in the lab before, you would know that it is virtually impossible to get the meter rule to be completely balanced and remain horizontal on the pivot. No matter how you place it, the meter rule is always going to be a little bit off balance. That's why the answer here is that it's difficult to obtain the exact balance, or you can write it's difficult to judge the position of the center of the load, or sometimes the load or even the ruler may slide. So these are actual practical difficulties in this particular experiment. Now, when it comes to the set square, sometimes set squares are provided and you need to know how to use the set square, even in theory. So a set square may be provided with any measurements that involve a meter rule, for example, measuring the length of a pendulum, the length of a spring, or the diameter of one or more round objects. Why we use a set square is because the set square has two sides that are perpendicular to each other, which makes it very useful. So to use it, we line up one of those right angle sides against a meter rule and the other right angle side to the position where we want to measure. For example, if we want to measure the length of a pendulum. To measure the length of a pendulum, if you can recall, we always need to measure the length up to the center of the pendulum bob. So to find the center of the pendulum bob on its own is quite difficult, but with the use of the set square, as you can see, it becomes quite easy to determine the center of the bob relative to the meter rule. So if you were required to explain or to draw how the set square should be used relative to the pendulum, this is an example of the drawing you can draw, of course with labels. You could also use the set square to help determine the length of a spring. So for example, as you can see, we would align the set square in such a position where this part of the set square would be pointed towards the spring. Now, whether using the set square to measure the length of the pendulum or the spring, the set square shouldn't be touching the pendulum or the spring directly because it could interfere with the measurement of the length. Rather, it should just come as close as possible to the pendulum or the spring. Now, to measure the diameter of round objects, the set square is very useful in this because using the meter rule to measure the diameter of a round object on its own is very difficult. By placing a pair of set squares in this position, we're able to get the diameter of the round object more accurately. This can also be used if we are measuring the diameter of more than one round object. So what we can do is if we have identical round objects like these, we line them all in a row with no gaps in between them and place a pair of set squares on either side to get the diameter across these round objects. To get the diameter of a single round object, we take the total length divided by the number of the round objects, meaning we're getting the average of one of the round objects. And that's how you can get the diameter in this case. Now, in terms of the spring, when measuring the length of the spring, you must remember you only measure the length of the coil and do not include the hooks above and below the spring. So if you measure the length this way, this is wrong. You only measure the length of the coil like this. So sometimes you may be required to show how you measure the length of the spring. This is the measurement that you would take. Now, for the oscillating pendulum, here are some common questions you would come across. For one, you might be asked to explain why timing 10 oscillations give a more accurate result for the period t than timing 1 oscillation. So in this case, it's something to do with the error due to human reaction. So the answer you could write would be that the timing errors due to reaction time become less significant, or that this error is spread out over a longer time. Another common question would be to describe one technique that you use to improve accuracy when measuring the time for 10 oscillations, and the answer you could write would be to use a fiducial point or to count from when the pendulum passes the vertical or start counting from 0. Now, another common experiment that is tested are experiments with optical pins. So they could be an experiment involving a plane mirror or an experiment involving a transparent block. So a plane mirror experiment is a light reflection experiment, while a block experiment could be a refraction experiment or total internal reflection if you're using a semicircular block. Now, regardless of whether you're using a plane mirror or a transparent block, the experiments with optical pins have pretty much the same precautions. So whenever you ask for a precaution, you can use any one or more of these. So when conducting the experiment, you should be viewing the bases of the pins. You should also be placing the pins as far apart as possible, at least more than 5 centimeters apart. You should also ensure that the pins are vertical or at right angles to the ray trace sheet. You should draw thin lines, use a sharp pencil, or use thin pins. By the way, if you've never conducted the experiment with optical pins, these are actually screenshots from my video which explain how to conduct these experiments. If you'd like to observe how these experiments are conducted, you can watch my videos. I'll place the links in the description below. Now, besides optical pins, other common experiments could include experiments with the ray box. For example, the light ray shining through a rectangular block. So for ray box experiments like these, a question they could ask you would be to suggest one source of inaccuracy in this experiment, even if it is carried out very carefully. So this is a screenshot from my video where I show how to conduct the ray box experiment. If you'd like to watch the demonstration, I'll put the link in the description below. For now, as you can see, the main problem here is that the light ray is quite thick. So although we've placed a thin slit in front of the ray box, the light ray still diverges a little bit, causing the light rays to be a lot thicker than we would like it to be. So the answer you could write here is with regards to the thick light rays. So the source of inaccuracy here is the thickness of the light rays, or that it's difficult to align the incident ray with FE, which is where the incident ray should be. It's also difficult to place the crosses accurately, and it's difficult to judge where the center of the ray is because it's thick. So these are actual practical difficulties with regards to the ray box experiment. Now the ray box could also be used in a different experiment involving lenses. As you can see, these are some past year questions involving the ray box with the lenses using an object made out of a cardboard with a triangular cutout. So this is an example of a precaution question with regards to this experiment. It says here, in this type of experiment, it can be difficult to judge the screen position that produces the clearest image. Suggest 2 precautions or techniques to overcome this difficulty. So the accepted answers here could include use a darkened room or bright object for a clearer image. And to obtain the clearest image, you need to move the screen slowly back and forth, or to approach the clearest position from both directions and get the average. So here's a screenshot from my video where I show how to conduct the ray box experiment. Again, if you'd like to watch the demonstration, I'll put the link to that video in the description below. There's a lot more, of course, that you need to know, most of which is based on practical knowledge that you should have gained in the past many years of learning science or physics in class. My recommendation is to do practice past year papers, a lot of them, and check the mark scheme to test yourself if you're able to answer the questions. So I've done my best to cover a general overview and provide you with as many tips as possible. Of course, you should be doing a lot of practice on your own. Anyway, I hope you found this video to be helpful for your upcoming examination. Do check out my videos on other topics you might find helpful. If you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. For notes, quizzes, and syllabus updates, check out my website at physicsrocks.com. Do subscribe for more free physics lessons from your physics teacher, Miss Ho. Happy studying and all the best for your upcoming examinations.